right? Is that useful?
No.
Why?
Because you just did that, now you're undoing
It undoes the exact action, so that's not productive. So are there other electrons I could move? How about I move these? I know what you wanted to do. I'm doing something else.
You won't.
I won't do that. What's that?
There won't be a bond there anymore.
If I do that, I no longer have the connection between the oxygen and the carbon. I no longer have the bond that I know needs to be present. That's interesting. When I'm moving electrons, there's only some electrons I can move. I can move the non-bonding electrons, and I cannot move those electrons. How are those electrons different?
It's a single bond, and if you take it away, then it's going to be a different molecule.
When I'm talking about moving electrons in our resonance, not single bonds. That says single. Okay? Which means that arrow is invalid. So, now that I've shown the bad example, tell me the good example that you are.
Take the double bond from the top. And
I just realized I had an extra pair of electrons there.
that confused me. And then move that into non-bonding electrons.
Okay? Now those would be non-bonding electrons. But I'm adding this arrow on a structure that doesn't exist. It's invalid. So I can't use the arrow on this drawing because this drawing doesn't work. Where does that arrow need to be drawn? On the top drawing. Now what does that mean? If I was to go through and draw the result, now in blue, the red comes in, forms the double bond. Good, what happens to the double bond? It goes up to make a pair of electrons up there. What have I now drawn?
The red structure.
The red structure. What I've now shown is how the black structure is related to the red structure using curved arrows. Those curved arrows are my effectively mechanism. In this case, it's resonance. How do the electrons move? In that moving process, we've pulled out some useful information. Number one, non-bonding electrons are the ones we want to move. Okay? They want to move short distances, atoms to bonds. I cannot move single bonds. That's bad. What else could I move?
Double bond.
Double bonds. What is a double bond?
Two pairs of electrons.
What is a single bond?
One pair of electrons.
When I'm moving the double bond, am I moving two pairs?
Just one pair.
I thought you said one pair was a single bond.
Oh, you're just confusing me.
Damn it. Our definition or our difference between single and double bonds is now very problematic. Okay? When we're talking about moving the double bond, quote unquote, we're only talking about moving two electrons. We aren't moving the whole double bond, we're only moving half of it. Okay? The single bond we're definitely not allowed to move, and that other half of that line I didn't draw, or I didn't move, right? Okay? So our definition of double bond is now very called into question. If we think back to that video where you're like, what the heck is sigma and pi bonds? Guess what? This is sigma and pi bonds. Sigma bonds are in reference to a single bond. Okay? And we'll talk about this hopefully later today. Sigma bonds are a direct connection between our atoms. Pi bonds are when we need to make multiple bonds. When I need to make a double bond, when I need to make a triple bond. I will take a single bond and I will layer another bond on top of it. But I can't layer it in the exact same place my sigma bond is, so I'm getting a different type of connection. At this stage, we call that connection a pi bond. There's a logic, there's a reason behind it, but we have to get to that reason. So when we're talking about our resonance, we are allowed to move our non-bonding, and we are allowed to move, as the screen shifts on me, pi bonds. We cannot move single bonds. In all cases, when we're moving our electrons, we're moving them in very short distances. We're going atom to bond. Dang, was the pi bond moving atom to bond?
It was bond to atom.
Ah, so we can do atom to bond and the flip. We can do atom to bond. Or I just said the same thing again. Bond to atom. Those are now the limitations in my resonance. It's bothering me I don't actually have it in the slide presentation. I'll fix that in a little bit. Kind of makes sense? Okay. So what does that mean we need to do if it kind of makes sense?
I have a question.
Okay. Ask questions.
Oh, sorry. For the formal charge, since we're just drawing the charges on each one, we're completely eliminating the need to do the brackets and the formal
Yep.
charge on top.
Brackets are irrelevant. We no longer have to worry about that again.
Okay.
Yeah. And to give you an idea of how important the brackets are, that is something invariably when I teach Chem 130, I forget to grade. Because that's how useless the brackets are. Yes?
Can you say your definition again for pi bonds?
So our pi, and we didn't really come up with a good definition yet for our pi bonds. Our pi bonds are another bond in addition to a single bond at this point. It's the addition of an extra bond, which would manifest in a drawing as a double bond or a triple bond. Those are extra bonds in addition to a single bond. And right now we're calling them pi bonds because we don't have an explanation of what they are or what makes them other than we know they're allowed to move, and that's about it. Okay? So we have to come up with some way to differentiate them. Okay? So, in our rules of resonance, what we need to do is find a source of electrons. In our last case, we kind of cheated because we had two structures, right? And we could say, oh, I want them to look the same, so I'm going to move those electrons over to make the double bond. That made sense. That was easy. What we need to move to is a scenario where we only have one structure. How do we know what the other resonance structures are? Okay? So in that scenario, what we're going to do is find a source of electrons. Well, what are our sources of electrons?
Non-bonding electrons or pi bonds.
Non-bonding electrons or pi bonds. Those are our only sources of electrons. Okay? And what we're going to do with those is move them in the immediate vicinity. The immediate vicinity being bond to atom and atom to bond. Those are our two choices. And as you might see, there's a potential box floating in there that we'll address with this potential example. Right? Once we've done a single movement, we have to verify that our octet is satisfied. So with our last one, we did that single movement, and what happened? Carbon exceeded its octet. We can't exceed octets. That's bad. So what does that mean? We have to fix that by breaking a multi-bond or pi bond, another one potentially. Right? If it's too few electrons, that's a slightly different scenario, and that's one that we're actually going to encounter with this example with our benzene. Right? I thought this actually showed all the carbons in it. Are we okay knowing that those are carbons? Okay, so guess what you get to do? Resonance. Your turn. Walk through these steps, see what you come up with. I'm going to come around and look at what you got, and we'll see what we get. And if you got questions, common for students to go through and do this. Say, okay, well, I'm going to take these electrons in that bond, and I'm going to put them on that atom so it has a lone pair. Okay? If all of that information is on there, you're saying this structure now exists, which means that carbon now has 4 valence electrons minus the 4 bonds minus 2 non-bonding pairs, or 2 non-bonding electrons, which means that carbon has a -2 charge. Is that really what you meant to say? No. Okay? So we have to differentiate as we move through. This means lots of drawing. You start with a structure, you say, what do I want to do? You show the action that you want to have happen on that drawing, and you show the result in a new drawing. Has to be done that way, otherwise things get way too confusing, and if you lose track of where you're going, you'll be wrong. Okay? Anybody reading it wouldn't be able to understand from the very beginning. Okay? So, that's the first thing to address. The next important thing to address. This question becomes significantly harder than the last question. Why?
Because you're moving it from
Okay? In the last question, we started with a non-bonding pair of electrons, a negative charge. That's probably reactive. Here, everything's neutral, so it doesn't stand out as anything particularly reactive, so we grab a pi bond. Okay? Well, how do we move our electrons in a bond? We go from bond to atom. That's our rule. Okay? What does that then mean? Well, if we drew out the result, what do we see? We've got all of our hydrogens around. All of those are static. Those have not changed. This is where one of the reasons why people get frustrated with OChem, because you have to draw a whole bunch of stuff. You have to draw everything all the time. You can't just stop drawing parts of your molecule. It all has to get drawn in. The rest of the structure didn't change, so I'm going to maintain those the same, get those finished. Once I've got those finished, I'll then address what my arrow said. My arrow said I'm moving a pair of electrons, that bond, and I'm putting them on that atom, which means I need to see a lone pair of electrons. That's immediately going to give me a negative charge, which is a bit of an overstatement on my part. But because I've done so many bonding patterns with things, I understand that it needs to build a negative charge quickly. We may not. How can we figure out that it needs to become negatively charged? What do we have to do?
Calculate formal charge.
Formal charge. How many valence electrons does carbon have? 4 minus how many bonds? 3 minus how many non-bonding electrons? 2. There we go, a negative 1. Cool, that makes sense. Was there another way to do it? Yes. What charge was the carbon to begin with?
Neutral.
Neutral. What does the arrow show?
Moving of 2 valence electrons.
That arrow shows 2 electrons are moving towards it. If it starts neutral and gains electrons,
Becomes negative.
it becomes negative. Okay? Why did it not become negative 2? It already owned one of those electrons that came across. It really just gained 1 from the other carbon. Okay? And that's why it's picking up a negative 1. So we can understand formal charge. Fantastic. Calculate that every time. That's tedious. We can understand arrows, what those arrows mean, okay, as far as the transfer of electrons and how that manifests in charge. Or we could straight up just memorize that if I see a carbon with 3 bonds and a lone pair, it must be negatively charged. 3 different routes. You have to decide which route is best for you to go through and solve. That is your choice, not mine. Okay? Is our structure correct? No. Why is it wrong?
You still have to move the other 2 pi bonds.
No. Oh, so you're challenging the whole general philosophy. It's not a resonance structure. Why is it not a resonance structure? When we do resonance, all we're doing is moving electrons around the molecule. We aren't adding electrons. We aren't removing electrons. We're just shifting where they're located, which means the overall charge for that molecule, if we're doing resonance, is the same all the way through. Our starting structure showed no charge, which means our ending structure had better be
No charge.
no charge, so we're missing something. What did we miss?
The formal charge of the carbon next to the negative.
Those pi electrons were shared between both of those carbons. You took both of them and put them on a single carbon. The single carbon that gained those electrons, yes, becomes negative. What happened to the other carbon?
Becomes positive.
It lost electrons. It needs to become positively charged. Okay? Now, have we drawn a resonance structure? Yes. And this is where we'll layer in, within our Lewis structure video, we said there were extra layers that go with it. Once we've got formal charges, there's an extra thing that comes with our resonance structures. Best, useful. Okay? Ideally, when we're dealing with resonance, we want all of our drawings, all of our structures to have the exact same energy. Well, what's going to dictate that energy? Octets and charges. This drawing that I have here has charges and it's missing an octet. It is a valid structure to draw. We haven't exceeded octets, but we're missing an octet. That makes this structure higher in energy than this structure. Generally bad. So what does that mean we should do?
Convert the rest of the structure.
We should keep moving electrons. Okay, what electrons should I move next?
From the pi bonds to, well,
Pi bond's not a bad idea, but I would argue there's a better choice. What electrons are you allowed to move in resonance?
non-bonding electrons.
Non-bonding electrons and pi bonds. So pi bonds is not wrong, that is valid. Is there another choice? Do we have non-bonding electrons?
Yes.
Yeah, we now do have non-bonding electrons. Which pair of electrons makes more sense to move? The pi or the negative?
We're trying to make a resonance pressure, so we can't just convert back to what we came from.
True, you're assuming something else. You're assuming what we do with those electrons. We'll address that in a second. Which electrons should we move? The pi, or a double, or the negative? It's more unstable. Charge is bad. Everything that we do is to try and neutralize charge. All reactions are neutralizing charge, okay, in one form or another. Which means if I see charge and I'm trying to draw resonance, that needs to be my focal point. And it can be the negative or the positive. Okay? The negative is easier to manipulate because when we talk about resonance, what are we moving?
Non-bonding electrons.
Electrons. The negative is electrons. What is the positive?
Not having electrons.
Not electrons. It's hard to grasp the motion of something that's not there. Okay? So it makes generally more sense to move the negative. So what we could go through and do is now move those electrons. There are multiple directions we could move those electrons. I would argue there are 3 potential ways. There's one in orange. This is going to be kind of hard to show. There's 2 in green, moving it up towards the hydrogen. Or 2 in green, or there's 3 in red. Everybody see that? You already said you don't like the orange option, right? Why not?
Because it's just converting back to what we came
Goes back to where we started, which means what should we do with the orange option?
from.
Yeah, we should erase it. I can't selectively erase very nicely, at least not that green one. The green one would be moving electrons towards the hydrogen, meaning we have a double bond to the hydrogen.
You can't do that because of it's whatever it's called.
It's octet. Hydrogen can only have 2 electrons. If I make a double bond, it has 4. Hydrogen can't do that, which means the green one makes no sense, which means
The red one.
we only have one option. We're going to go with the red one. If we do the red one and we started to draw that out, what are we going to get out of this? We haven't touched anything else, which means everything else is there. It's all drawn in. And there in blue, we'll show that new bond. That positive charge, we didn't do anything with that positive charge. It's still there. So we'd have that structure. Anybody have an issue with that structure? You do. What's the issue?
On the left, hydrogen has exceeded the octet.
Right idea, wrong word. You said hydrogen.
Oh, carbon, sorry.
The carbon in the middle of that has exceeded its octet. We are not allowed to draw that. This big ugly one with all the charges, we're like, there's got charges. Yeah, that's okay. We haven't exceeded the octet. We haven't done anything illegal. This drawing is illegal. So if I did that, I would have to recognize that I have to simultaneously move that pi bond to the atom. So we can go bond to atom. Kind of make sense? So we would have 2 arrows this time instead of 1. I really did not want to erase that whole structure. God damn it. Those of you being like, yeah, don't you have an undo? I do. Whoops, not there. With contrasting color, there's our negative. There's our positive still there. There's our double bond. Okay? So from that structure, we took the negative, we made the double bond. Ta-da! We had to break that double bond by moving the electrons from the bond to the atom. Ta-da! Yeah? We good with it? So we have yet another resonance structure. Is this one as good as the past one, the one in red? Green versus red. I'm going to take the pause to mean that's a hard question, so let's switch it up. Green versus black. Which one's better?
Black.
Black. Why?
More balanced?
Not good enough. Why is the black one better than green? Why is it more stable?
It's neutral.
And neutral gets a little bit shaky. Were you saying neutral too, or were you going to say a different word? You're not. I know what you're trying to say with neutral, but that's the wrong word, because the green structure is neutral too.
Doesn't have a charge.
There we go. Okay. The green structure has a negative and a positive, so that structure is neutral. It just has charges balancing out within it. Okay? So the green structure has charges, the black one does not. So the black one is better than the green one. Black one's also better than the red one. How about red versus green? They're the same. We've changed where the charges are located, but they're the same energy. They are both charged. They both have a carbon with a negative charge. They both have a carbocation. They're roughly the same. So these two would be equivalent energy resonance structures. Okay? Now we're going to add an extra little layer in here that's going to address this kind of box, and it's going to address what I believe people are already starting to draw, though a bit premature for this. Okay? Take a look at the black structure and the green structure. And I want you to take a look at those very, very closely. So much so I'm actually going to delete the red structure. Can I add arrows to the black structure to make it look like the green structure? What would I need to do?
Can you add like multiple arrows showing multiple steps?
Can I do multiple arrows? Yes! I need specifics. Like, I can draw arrows all day. Like, where am I drawing them?
An arrow. So we're drawing on the black one, right?
Yeah?
Okay, so from the pi bond on the top, an arrow to the carbon that's on the left of it, and then another arrow from that carbon to the single bond on the left of it. And then the pi bond that's on the left, an arrow to the carbon that is next to it, below it. And I think that's right.
Everybody agree? Does anybody want to be like, is that really how I have to do this?
It's gonna be a lot of arrows.
Oh, I wonder if there's an abbreviation. Is there a shortcut we could do? Is there something like, perhaps, where I could take the pi bond and instead of moving it from the bond to the atom, I could just be like, let's just go to the bond? Can I do that? Yeah. That's lovely, isn't it? That gets rid of all those arrows, and we can just go bond to bond. That's what's in the black box. We are allowed to go bond to bond. We have to be careful with it, because it's not saying from this bond to this bond, or this bond all the way over here. That arrow is saying bond to the bond right next door. It's connected to that same space. Very, very short distances. You're not jumping across the molecule. Does that make sense? Okay. Why is that going to be particularly helpful for us? Well, we can continue to do this bond-atom stuff all the way around, and that's fine. And what we're going to keep drawing is these charges with these structures with positives and negatives. If we take a step further back and continue that a little bit further out, what we'll note is that we could go bond to bond, and we could go bond to bond, and we could end up drawing, with those 3 arrows, a new structure. This new structure would look something like this. Are all the double bonds in the same locations?
No.
No. They have all equally shifted around the molecule. How did they shift around the molecule? The electrons moved from bond to bond, bond to bond, bond to bond. Because the molecule was also cyclic, that allowed those electrons to all just kind of shift one location all the way around and the molecule to remain neutral. This is a very particular scenario. What we're looking at here is the functional group known as an aromatic ring or a benzene. And benzenes are so incredibly stable that they don't react with other things because the electrons are constantly moving around in a ring around that molecule. Okay? Which of those structures is the correct structure? Both. Okay? And that becomes a dilemma again with resonance. This is where sometimes what you'll get is what's known as a hybrid structure, which I'm not a big fan of, but there are certain scenarios where it makes sense, and we could see the circle in between. That's very commonly how we would draw benzene. What is that circle representing? The double bond can be at any one of those positions all the way around the ring. It's being equally shared. That as a hybrid structure is a neat idea. It becomes problematic because what we talk about in OChem is how do things react? Well, what's reacting? The electrons. Where are the electrons if I've got a circle?
Somewhere.
They're somewhere. That makes it hard to show where the electrons are coming from because they're just somewhere in the ring. That's challenging. That's why I would push away from hybrid drawings and stick with a static resonance drawing. Okay? Whether or not it's the correct drawing, you will find it depends on the scenario that you're trying to do. Okay? And this is where looking at the worst or the best worst drawing can be very beneficial instead of looking at the best drawing. The best drawings, as we've shown here, show no charges, so we don't see any reactivity. But if we look back at the ones you've got drawn in your notes with the charges, you see a positive and a negative, which means if I can find a positive and a negative somewhere outside that molecule, I'm going to connect to one of those two spots. I can predict chemistry by knowing those charges. So those bad resonance structures are actually the most useful for us for predicting chemistry. Make sense? If we were to go through and do it, another example, this is one I would highly encourage you to do on your own time. Go through and start with this structure with it as a positive charge. The very first thing we have to do is the very first thing we do with all Lewis structures, which is valence electrons. Okay? How many valence electrons belong in this structure? Well, there are 2 nitrogens. Each of them has 5 electrons.
But there's 3 nitrogens.
There's 3 nitrogens. One of them is supposed to be an oxygen.
Oh.
So there we go, an oxygen. You'd still be able to do it if they were all 3 nitrogens, but the oxygen's a little bit more fun. Carbon has 4 valence electrons. The oxygen has 6. There are 4 hydrogens.
Oh, there's 6.
Fuck, an oxygen. There are 5. I was still wrong. 5 hydrogens. Each of those has 1 valence electron, 1 oxygen, 4 carbons. And then we have to account for the charge. What does the charge mean? If it's a positive
Plus
charge,
minus 1.
it's a -1, because what we're talking about is counting our electrons. If it's positively charged, we had to have lost an electron. So we now do all that math. We get 10 and 4 is 14, 6 and 5 is 11, minus the 1 gets me a 10, and I get 24 electrons that have to go into this drawing. How many electrons are already shown within this drawing? 16, which now means I need to account for the remaining 8 electrons. Where should I place those remaining 8 electrons?
Not on the hydrogen.
Not on the hydrogen. That's a good answer. I accept it. Where should I start placing them?
The nitrogen?
We've got 2 answers, oxygen versus nitrogen. I'm going to say I like oxygen. Why do I like oxygen?
There's not enough electrons on it? Or it's not
Nope, nitrogen has the same issue.
Only has 2 single bonds as opposed to 3 single.
So you've memorized bonding patterns. Okay, that's an acceptable answer. There it is. Oxygen is more electronegative. Because oxygen is more electronegative, I should be placing the electrons up to its octet first. That means I need 2 lone pairs. Each of the nitrogens get 1 lone pair, and I now have a potential Lewis structure. Why do I say potential? What do we have to do?
Resonance? Well,
It's on a resonance slide. You'd be like, we got to do resonance. But why do we do resonance?
because there's double bonds, pi bonds.
So a pi bond right now we would recognize because we have a double bond. Do you see a double bond?
We need to check our octets.
Ah, there's our step. We need to check the octet. And if we check the octets and we zero in real quickly, that carbon is missing its octet. That's now a bad drawing. Is there a way I could stabilize it? What would I need to do?
You can move from either of the nitrogens.
I can move electrons from the nitrogen or the oxygen in to make a double bond to satisfy the octet. Is that going to change charges? Yes and no. That's why I want you to go through and do it on your own. Kind of make sense? That would be a good question that if you come up with questions, you can ask whatever it is, next week, Thursday? Ask Thursday, not next week. Okay? Or you could ask in the tutoring center. But I'm going to leave you to kind of resolve that one. And the follow-on question is deciding which of those structures is best.
Is the charge negative one?
Charge is positive one.
Okay.
Why are we doing negative one? What is the 1 counting? What is the 5 counting? The 6 counting?
Valence.
Keep going.
Valence electron?
Electrons. What charge are electrons?
Negative.
If I'm positive, what do I have to do?
Make it negative?
I have to subtract an electron.
Oh, okay.
That's where that number is coming from. Okay? I will say that is probably one of my favorite questions to ask. I think that's a good thing for you to make sure you're comfortable with.
For that one, are we looking at, we probably don't want me to ask this now,
No, you can ask.
3 different resonance structures?
Maybe. So maybe you were looking at 3 different resonance structures. That would be a good thing for you to kind of piece through and see. I'm actually going to get into the slideshow now. Common bonding patterns. So you called out that your oxygen, you know, has 2 bonds, okay? And therefore you need to satisfy your electrons. So you've started to memorize bonding patterns. That's good, okay? Typically my recommendation, or how some classes run Lewis structure for OChem, is they give you hundreds of Lewis structures, right? What happens after you draw those hundreds of Lewis structures? Memorize the common bonding patterns by having done it so much work. Okay? I prefer to just say, you should know your common bonding patterns. You need to practice Lewis structure. You've got to decide your comfort level with where the Lewis structures are. If you know the bonding patterns, you don't need tons and tons of Lewis practice. You just need to acknowledge where the common bonding patterns are. Kind of make sense? The next part is dealing with shape. So if we consider methane, and we were to draw out a Lewis structure for methane, hopefully you would all relatively quickly get to something that looks like this. And we kind of touched on this. We said that the bonding angles in there aren't accurate, okay? Because if we look here, that looks like a 90-degree. Whereas if I look here, that's 180 degrees, which means the bond angles are not all the same in this representation for the molecule. Well, all the hydrogens are the same. There's no extra electrons in there. What does that mean? That means Lewis structure failed. Lewis structure failed to accurately represent the 3-dimensional model. This is where valence shell electron pair repulsion theory comes in, and was effectively saying, I know how many groups of electrons there are around this. What shape has to come out of that? That's why they generate the shapes that come out of it. Okay? Those shapes get names associated with them. Tetrahedral, trigonal planar, linear. Some of those names are a little bit, trivial is not the right word, obvious. Obvious is a dangerous word too, but easier to recognize. Trigonal planar, because they're three things, and they're all on the same plane, like a piece of paper. Tetrahedral, depending on if you play D&D or not, that tetrahedral makes sense. Right? If you haven't, well, I don't even know what that shape is. Right? The context behind those kind of changes. You're responsible for knowing those. Right? And ultimately what they are is really just a human invention. We looked at it, said this had to be true, so we said it and it existed, and that's how it worked. Okay? We do encounter some problems with this or refinements, bonding versus non-bonding, which means you get more shapes that come out. So when we talk about Vesper, you're pretty much sitting in the 120 and the 109 range. The linear one to me is just obvious, so we kind of just ignore. But everything else is sitting in these kind of categories. You're responsible, not necessarily for knowing the shape. So for the first test, I will admit I will probably ask questions. What is the shape for this molecule? Okay? Because that means you know how to draw the Lewis structure, you know how to differentiate within the Lewis structure bonding versus non-bonding, and then identify the shape. The most important aspect out of this shape is knowing where the electrons are located in space. This is our three-dimensional representations. This is where model kits come into play. So if we're looking at methane with those 4 bonds, what we've got is not a thing with 4 lines all the way around. We've got that weird goofy shape with bond angles in between not being perfectly 90 but slightly larger. That's the 109.5. Knowing that it is 109.5, again, I don't really care. What I care is that you know that it's not 90. And if there's this shape associated with it. Okay? Next thing we'll kind of address with the NH3. NH3 has 3 bonds. So if this was my NH3, what do? Remove a bond, and I have now NH3. Why does it not go planar? Well, in the NH3 octet, there's an extra pair of electrons that's still occupying that space. Because it's occupying that space, we're still forced into the tetrahedral geometry. But if we looked at it, there's our electrons. We call it trigonal pyramidal, not tetrahedral. Why? Bonding versus non-bonding. Why does that matter? Where is the bond versus the non-bond of electrons? When did we start?
What?
When are we done?
15.
Okay, I guess we're done. Where are they? If I hold on to this atom versus I share it with somebody else, where does this go? I know it seems kind of weird. If I hold it versus I'm sharing it, what happens? The distance of where those electrons are located changes. If I hold on to it, I have it close to me. If I share it, those electrons are moved further out. Bonding electrons have the electrons moved further out. Non-bonding electrons move closer. So if this is a tetrahedral structure, there's that top part, and I move my wrist closer, what do these electrons do? They need to move. Those are electrons. What happens when electrons get near electrons? They repel. Where can they repel? Whereas if we remove those electrons, what happens? And they move into, my hand doesn't do it very well, a trigonal planar shape when those electrons are entirely gone. So what we're looking at is those electron repulsions, be them bonding or non-bonding, and that's what tweaks the shapes ever so slightly. And it's also going to tweak the bond angles within. Does that manifest and show up in our chemistry? Yes, it absolutely does. Will it for you? I don't know. We'll see. with that, I definitely have to stop. Because we gotta walk all the way over to the lab.